Well, hello. So we're back. This is the second video in the new paper series that I'm thinking I will start. I think I've begun. So I'm Parakam Gupta and I will be trying to explain a very basic swarm formation method. If you've not seen the last video, you can find it in the cards, but I'm going to briefly go over it, and I think it should be enough for you to understand the basic concept of what we're doing here, and then we'll move over to MATLAB for an implementation that you can check out, and I will put the code in the comments or in the description, sorry. Yeah, let's start. So suppose we're going to do three things here, right? When there are robots, the first thing you want to do is formation. Yeah, my penmanship isn't the best, as you can see. So suppose you want to, what you're essentially doing is you're saying, you're just adding up the components of where things should be and where they are. So suppose you have, say, this over here is your world frame, and I tell my, this is the x-axis, this is the y-axis. So I tell my robot number 2, please go into the formation such that you are 0, -1 from robot number 1. So you can see that this is robot number 1. We are supposed to be, so the red vector is what we're supposed to have, right? So we were supposed to have, from robot number 2, we are supposed to have, what is this in the x-axis? It's suppose -1, 0, right? So your relative position should be such that robot number 1 is on your left. So when it is not, what you do is you say, okay, it's supposed to be that. That's my reference. And what is my current vector? What is my actual vector? So you say, okay, my actual vector is this here. So what do I need to do? I just need to move towards 1 relative to the difference. So you say reference vector minus position in x, position in y, current one. Right, so you're basically saying, I want to travel this remainder distance here, denoted by the blue line, by the blue vector. Then you repeat this for the other one. So suppose I draw now a new reference where I say, please have robot number 3 such that it's at a position of 0, -1 from you. So 0, -1 would look something like this here, right? And well, actually the robot is here, right? So what do you do then? You say, okay, I need to move this path to cover it, right? Because if I move through that path, I will get closer to my goal. So what you're doing recursively is saying that, okay, the robot number 2 needs to move this, and the robot number 2 also needs to move like this. So essentially, you just take the resultant vector, which is suppose something like this, right? And you say, okay, I'm going to follow this path. So this is the path for robot number 2. You do this recursively for every robot. So now what's going on is, this robot wants to move here, this robot wants to move here, this is robot number 4, sad and alone. It's going to move here, and this is going to move here. Now what we do usually is we take this difference and we multiply it with a factor, suppose k position, such that we get a velocity. So what is happening is, because 1 here is the one that is the furthest from the swarm formation is going to move towards this swarm with a bigger vector, because obviously it has a larger delta, and each one of these 3 robots are going to move towards each other. Everybody moves towards each other, and this difference recursively becomes a formation. So once this whole thing works out, you get a formation that looks something like this here. One moment. Right. So you get something like this. Again, bad penmanship, but I beg your forgiveness for that. Okay, we need it to be bigger. So we have robots here now. Okay, so we've completed one task. Understood, right? We are taking difference of the position vectors and we're saying, okay, you are this much further from where you need to be, so please go there, which they have gone, and your first step has now brought you to the second step. Second step here. So this was your formation. Now it would be about moving the formation. Although I am showing this as 3 steps, they're all happening all at the same time. Now you're here, right? But suppose you need to move your formation right over here, somewhere here, like this. Okay, this is supposed to be snapping. There you go. So suppose you need to move it here, right? So then again we go through the whole simple process of first we find our centroid. So we know that our current centroid is situated here, and then we say, okay, what is the other centroid that we need to get to? We need to get here. So all we do is we say, okay, this is the delta between the centroid here, again shown in blue, right? I need to get there, and you again multiply it with this vector with suppose formation control or centroid control constant. This would give you a value, say velocity vector, and you just add it to everyone's velocity. So what you're doing essentially is you're saying the whole swarm moves as a group here, and this one moves in this direction, this one moves in this direction. I know I'm not drawing them parallel, but they're supposed to be, and in that direction. So the whole thing moves over and we get our new formation like this. Here and here. Perfect. This brings us to the third thing. How do we avoid collisions? So remember I told you about the potential, how we have potentials, and basically what we use is we use electric potential, or we simulate electric potential. So collision avoidance is what we have to do next. I mean, not next, but it's all happening all at once. So what we essentially say is, when these robots are, say, here and here, while they are outside our specified radius RS is equal to suppose 2 meters, do not repel them. But if they do come within 2 meters, so suppose they come to this position here and this position here, you have to start repelling. So you go through this, right? 2 meters. Then you put this in a potential function, which I will show you in the MATLAB. And you've got repulsion that goes up with the value exponentially high. So you basically get a force vector here, and this force vector, suppose I'm at this point here, so you get a force vector. So you take that force vector and you again multiply it with an alpha, which is also part of this whole function that I will show you. You take this and you say this is my force. You want to multiply it with something else, you can, and then you just apply that force on every robot. So you get force here for repulsion, Fr, and you get the same equivalent force Fr. Now I'm showing this to you for 2 robots, but you're basically doing this for every robot in the formation, right? So these are the 3 basic things that you need to take care of when you're building a formation. Now let's move on to the MATLAB. We've moved over to MATLAB, and let's begin without any delays. So first thing we do is we generate a random position. So I'm going to start commenting these so that I will upload this code and you can go check it out. So first thing we generate is random positions for starting of the drones, right? Then what we do is we say, okay, where do we want the drones to go? So I have given it an initial formation of a hexagon, and as you can see, this is the first coordinate, second coordinate, third coordinate, and so on, 6 coordinates. I'm doing this for 6 robots, and you can see 6 coordinates for the formation of a hexagon. The next thing we're doing is we're going to say that this is the matrix where we store our positions during the loop, right? Because one will be the position of the drones at every moment, and the other positions would be the complete arrangement of positions. So across, when the time moves, you want to collect those positions so that you can plot them at the end. So basically for plotting, right? That's where we do collect them, and then we go for force collect. I beg your pardon again for my bad naming of the variables, but please bear with me. I'm sure you would understand this as I go and explain. So this is the matrix where we store the forces experienced by each robot for plotting. Again, if you want to plot it, yeah, this is the force vector that I am temporarily writing down. So we will use it here to find out what the force should be on any given quadrotor or any given aircraft. Okay, here, so let me write this. This is the temporary force matrix to be used for every robot, aircraft, drone, whatever. Then RS, like I said, this is the activation radius for our force of repulsion. If you're within this radius, here you will experience no repulsion. If you're outside this radius, I mean. Then we have the timestamp, time chunk that we are simulating to be going through, right? Because suppose you're running this whole control mechanism 30 times a second, which is what I'm doing here, right? So this becomes 30 hertz or 33 if you're very savvy into what it actually is, right? Here it would be 33. So you have about 33 hertz of looping frequency for this control loop. This here is the control for the formation control gain, right? I'll show you what this does is, so basically this formation control here would decide how much force or velocity converted into velocity would be applied to the robots in order to move towards the formation, right? And this centroid is the formation movement gain, is what I'm going to call it. Kc is equal to 3.5. Now, as you'll see, basically these gains and these forces would be fighting among each other, because one of them is asking to make formation, the other one is saying no, we need to move the formation first, and so they're all going to happen together. Now this is the number of robots we have. Again, alpha. Let me give this a value. Okay, I'll give this a value in a bit because I need to demonstrate what happens when there's no repulsion force. So this is the repulsion gain, and this is the repulsion ramp game. Okay, so how quickly does repulsion scale up, right? And this is where we begin to do something. We are plotting our final destination or formation goal, which was, remember, a hexagon centered around origin. This is when we say don't erase the things on the plot, keep them there, right? Because usually standard behavior for MATLAB is we delete the plot when we plot again, plot the new points. This is a way to say please iterate from 0 seconds to 10 seconds and go through a dt of 0.03. So your values returned would be, say, 0, 0.03, 0.06, all the way up to 10. Okay, so you're gonna get approx what, 330 iterations approximately, right? This is where we store this is the velocity matrix for every instance that we're populating, because we need to find out what our velocity should be for the aircrafts to move or for the drones to move. This is the force vector matrix, as you can see, 6 by 2, because 6 robots and 2 dimensions, x and y, as similar to the velocity matrix for every instance, right? Then we go through the robots. Now here I should say n, bad programming, n. We go through n robots. We say that our temporary velocity is 0, right? Temporary velocity variable 0. We go through another for loop for n robots, and then we say, okay, what is the temporary velocity of this robot, right? You remember we're doing this for each robot. We're saying for every robot, what is the position that it should be in? So this highlighted section here is what is the current position, right? This is the position vector, relative position vector of the jth robot with respect to the ith robot. So for every robot, suppose we're doing this for the robot number 1 right now, we're saying for the first robot, what is the position of, so this j is iterating right now, right? Because we're in the inside inner loop, we're saying what is the position vector of j with respect to I for the first robot. So you go through all of them. You say with respect to first robot, doesn't matter, it will be 0. For the second robot, there is something, what is the current one? And then we go ahead and say what should it be, because we have specified the coordinates of these robots in the world frame, and in order to find the relative position vector, you can just take their final position and you can subtract it in the same way. So basically you're saying what it should be versus what it currently is, right? You just add all these vectors together and you store them in dvtemp. So apart from the future, I have to interrupt and check something. Suppose let me run this a little bit. dvtemp, right? So yeah, you see how I made a mistake here. dvtemp, it's supposed to be a two-dimensional thing. It's supposed to be a two-dimensional vector, although you know MATLAB healthily takes care of this for me, but again I cannot mess this up. So yeah, that's my correction there. And yeah, let's proceed. So we have dvtemp here, and we collect the velocity in a vector as a vector form, and we basically right now it's just the difference of the position vectors, and we're summing all of them together for one robot, right? What we're gonna do with that, we'll see later. Now here's the one, right? This is the force equation, right? So what we say is activate the force, remember RS, activate when below RS distance. Now what I'm doing is, first I'm checking, because you see how J and I can both be the same robot, and in that case the norm is going to give you NAN, and that's not good. And so you want to check if that's the case. If it's the same robot, please ignore it. So it better be not be NaN, and it should be less than RS. So norm is equal to basically taking your Euclidean distance and you're checking if it's less than RS. You're saying, okay, then the repulsion force experienced by this robot is going to be what? This is actually a scalar force. Okay, I'm calculating the scalar force based on the RS. Then I'm saying this is my alpha, which I've set to 0 right now. This is my gain, and this is my exponential function. So as this norm of, as they become closer, and the closer they get, the higher the force gets. It's multiplied by beta, negative exponential, right? And you have another one here. This is a standard form of, I think it's called Morse potential, and it's beta into RS here. So this complete expression here, you should go check back in the paper for the expression in detail, will give you the force. So this is the scalar force, right? Then you have, now you've only calculated the scalar version. You need to find the vector version. So for the vector version, what we do is, you know how we calculate the unit vector? So I've taken difference of the vectors and I've divided it with the norm of those vectors to find the unit vector. And then I break the force down into the unit vector. I mean, here I'm kind of doubling the force by multiplying it, or increasing the force by directly multiplying it like this. But all I'm saying is, I take a direction vector, find its unit vector, and multiply the force with that. So basically I'm getting a force in the direction of interaction of J and I is what I'm doing. So for each interaction, because remember we're in the inside loop, we are taking the scalar force and we're vectorizing it and adding it into a temporary force for that robot. So vector force is, we are vectorizing vector force. Then we say, obviously, if these conditions are not satisfied, the force is 0. And here's the next bit. Now we have stored our velocity of the robot right now, right? Because we had this velocity matrix. We've stored the current velocity that we just got, the x coefficient. So velocity x and velocity y for each robot here. Let's go a little bit quickly over this, and then you have the force matrix, which we're doing the same thing. We're collecting the force in scalar and we're collecting the force in vector. We're assigning the force temporary here at the vector form, and we're also collecting those vectors to find out what's going on. Next thing is centroid. Now the centroid that we want to get to is, this is the centroid we want to go, no, wait a second. Sorry, yeah, so this is just the initialization of a matrix, right? I've just assigned it to be a 1/2 matrix of zeros. Then I say go and find the centroid of the formation. So for that you just sum over the positions and then you divide it by 6. So this is calculation of centroid here. Then you say, okay, now, okay, this is the important bit. This here is where we're calculating the velocity of our robots. So what we say is the next position of the robot, calculating the position of the robot. So the next position is position currently in x plus velocity in x into our formation gain minus the centroid. Now it looks like a minus, but what here actually is happening is like a plus into goal centroid and minus your actual centroid, right? Because you do a current, your goal minus your current when you were trying to control things. It's the standard notation. So here, but we know that there's a hidden 0 here, because as I told you, here this is an initial formation of an hexagon centered on origin, as you will see soon in the plot. So that's where we get that, and this is our centroid gain, our formation movement gain, so to say. This is our force vector straight up, because we already multiplied it here with alpha, and then you just multiply with time instant. So basically velocity into time, right? You get your position and you add it. Then you're just collecting the position, so you're just assigning it into an array, filing it into an array, and then you're starting the plot. You plot it, you turn on the hold, plot it, turn on the hold, you pause it so that it looks like an animation, and then you run the code. Now let me show you what happens when we disable centroid. First thing, 0.0, so we have this here. See, they're moving into formation. Now once they stop, I'll show you something. Okay, is the run finished? It's still running. They're moving slowly, we can't see them. Okay, it's finished. Right, so if I zoom into this, you'll see here that they've neatly arranged themselves into a hexagon. 1, 2, 3, 4, 5, 6. Right? So 1, 2, 3, 4, 5, 6. Right? This is a complete hexagon that they've made. But as you can see, they are not going towards their actual position, which is supposed to be now. See, we've completed the first step like I showed you. Right? We've gone into formation, but here's our goal. So how do we get to the goal? We say let's have a formation control gain. So this will move our formation, right? Let's see, and you see they're moving now, and slowly they're going to converge to the positions they need to get to, and voila, that's it, they are in their positions. Let me zoom in. So you see how, oh, they just missed it. If I had run it a little bit longer, they would have gotten there, because it's minuscule force by the end. So you can see how their trajectories begin here, and you see how the blue one takes a turn. It takes a turn because it was initially going to go meet the swarm and go make the formation, because you can see that the formation control is 0.15. It acts very strongly because they're far away. So they first try to move towards each other here, right? And then the blue one, once it is sufficient, the centroid force, the force that moves them towards the centroid, takes over, and that's when the blue one turns. Now you see that it doesn't collide. It has no collision prevention right now because there's no repulsion. This is set to 0. Now you'll see something. So you remember how originally they were not getting to their formation? I'm going to do this. I'm going to increase the factor, and see, now we're going to see them move faster, and they're going to get to almost there, and they're there. So there are two ways, right? Either I can increase the velocity, or I can increase the number of seconds that I run this formation for. So you see, they're closer now. Now in order to have say more, even higher velocity, so I can say that this is 8 here, 8. Okay, so we're doing it again. Oh, a little bit better results, yes. Yes, you see, KC was the one that was supposed to get them in place, right? Yes, KP was the formation controller. So, yeah, so as soon as I increase KP, yeah, you see it, say they've reached. That's what it is. So that's the magic there. Now we're saying, okay, what happens with alpha? Let's start with the value. Let's see if they should repel. And I've set the RS to 3.0. That's not enough, because they won't repel. The sides of this hexagon are not further enough, so they will never trigger the force. So I'm going to set it to 1.0. This is the ramp, and let's see, you'll see the collision prevention here in a moment. And looks like there was no reason. change the motion, right? We're going to try again with 2.5. Let's ramp this up a little bit, and now you're going to see things happening. Aha, I see a little bit of deviation. In order to increase this a little bit, I would have to change something here. Must be deviating. Okay. So what I'm going to do is dial this down, and we're going to see, because what's happening is these forces take over compared to the repulsion. Now if I run it, you will see something. There it is, here. See, the repulsion force is really high, so they're all repelling each other instead of getting there. So you see how they're not going to make it to the formation, but to the centroid, but you see the repulsion forces here. Do you see this diversion that this pink robot has taken, and the blue one? Because they were going to collide, so they made that force in between them. That repulsion force has what's gotten things to work out, right? And let me add the repulsion force from much further away. So within, say, 3 meters, they're going to start to repel. So you'll see the same thing. Yeah, you see how the red one stopped and how the green one deviated. Here's the blue one deviating a little bit. They're all changing and adjusting their courses a little bit because they're already experiencing the force of repulsion from one another. Right? See, the red one again has changed. So that's what we're looking at. That's exactly what we're looking at. So this is here, again, diversion to repulsion, repulsion, again repulsion, here's repulsion, more repulsion, right? So that way they avoid collision. Now, yeah, let's just dial down this a little bit, and this a little bit. Maybe I'll dial this down a little bit more. So now they're just going to really struggle getting to their position. Let me see this. Let's see if this will work. Really fast. Oof, they're moving really fast. And yeah, look, they've gotten there. Yes. So that's about it. That's the lecture from today. And to stop this. Right. So I'm going to upload this file. You can all check it out and let me know. So hello everyone. I hope you liked all this. This is again an experiment that I'm doing. Maybe give me feedback on it. But before that, I would like to apologize a little bit on not realizing that the sound signature between my tablet's microphone and my laptop's microphone would be that different, and also I didn't realize that the keystrokes could be that irritating through the laptop microphone, so that's on me, and I'm gonna be more careful next time. Apart from that, I've talked about the other section of the code. There's another code called swarm_condensed that I might need to explain, depending if you understand Laplacian matrices or not. So please write in the comments and let me know if you'd want a third video that explains that section of the code. I would want to do it as well. If I had to talk about the future, I would say that if you can give me more ideas about what you want to be covered in robotics, maybe like ROS, reference frames, papers, in drones and UAVs, that's my domain. So that would be nice, and yeah, I think that's about it. So I think I'll get better in this whole editing and all the transitions and everything. Then I would say that if you like the video, please press like so that I can understand that how you feel. If you dislike the video, press dislike, but please also leave a comment that can help me improve this. Change things that you do not like so that I can tailor it more, and that would be very helpful. And yeah, maybe comments like pace of things, depth of things, details, and maybe background music if you wish that. I mean, That would be nice for me if you could suggest background music. Yeah, that's about it. I think subscriptions can come a little bit later. I'm not going to ask you to subscribe yet. I don't know how this is going to fit into all your subscriptions. But yeah, I'm going to try and see if I can impart more and more information from my field out to people so that they can come into the field and contribute and learn. Because it looks like a difficult thing, robotics, but it's just a series of things that you have to learn and understand. It's intuitive, it's fun. So I hope I can bring the fun to you. So that's about it. Thank you so much for watching.